Okay, so let's pick up where we left off last time. Um, in the question we're looking at here, we're going to be using Q to figure out what's happening with a particular reaction. Okay, so everything comes back again. So let's take a look at this question. Okay, so we're mixing these two reagents together and we want to know if a precipitate forms when we mix this solution. Okay, so we want to do a few things here to start with. We need to know, first of all, if any insoluble product will form when we mix these. Okay, so we're going to look at the components here. We have our lead ion and our nitrate ion. Okay, and we have our sodium ion and our bromide ion. So we do our crisscross here to see what products can form. We see that this is going to form NaNO3, which is soluble. And when lead and bromide ion combine, it's going to form PBr2. PBBr2. Okay. This can form, this is a solid, okay, and this solid is going to have a corresponding KSP, which would technically be a value given to you. You're not going to have this memorized. But if you look up this KSP value in the table that you have in 18.2, I think it is, that KSP is 4.67 times 10 to the negative 6. Okay, so to figure out if a solid is going to form, we're going to calculate Q and compare it to KSP. And we're going to figure out whether the precipitate forms based on this. Okay, so how are we going to calculate Q? We are going to look at the dissolution process of the PBr2 solid. And we're going to form a Q expression based on that. Okay, so Q is going to be equal to the concentration of Pb2 plus times the concentration of Br minus squared. Okay, so we're going to look back at our initial concentration values to fill them in over here. So our lead concentration is going to be 0.0150. The concentration of our bromide ion is 0.00350. And we want to square it. So our Q value is going to be 1.84 times 10 to the negative 7. So now we're going to compare our Q value to our KSP. And if our Q value is less than KSP, no precipitate will form. Okay, so we're going to need a higher concentration of ions to get that precipitate to form. Okay. Let's look at our next question. It kind of builds on this concept. I put this one in 3 parts. Okay, so first we're looking at this, the magnesium and calcium ions present in seawater, with the concentrations there. The ions can be separated by selective precipitation with potassium hydroxide. What minimum hydroxide ion concentration will trigger the precipitation of magnesium? Okay, we'll start there. Just going to write down some of these values. Okay. And we're doing selective precipitation by adding OH minus. Right, so when you're doing this type of process, this selective precipitation process, you want to actually use the KSP values of the solids that would form to figure out which one is going to precipitate first. I mean, they told us in this case that we're looking to precipitate or to trigger the precipitation of the magnesium ion, but there's a reason why they're focusing on the magnesium ion first in this question. When magnesium combines with OH minus, it's going to form MgOH2 solid. When calcium reacts with hydroxide, it's going to form CaOH2. Okay, so if we look at the KSP values of both of these things, we're going to see that they're very different magnitude-wise. So the magnesium is 2.06 times 10 to the negative 13 KSP. And the calcium hydroxide KSP equals 4.68 times 10 to the negative 6. And a very small KSP means that the concentration needed to precipitate the solid is very, very small as well. Okay, that's why we're going to be able to trigger the precipitation of the magnesium ion first. We're going to be able to form this solid with less of a contribution of the hydroxide ion. Okay. So we just want to, the first question asks us, what's the minimum hydroxide ion to trigger the precipitation of the Mg2 plus? So we're going to use this KSP value to figure that out. We know that the KSP equals 2.06 times 10 to the negative 13. Just look that up. And the KSP for MgOH2 is going to be equal to the concentration of magnesium ion times the concentration of the hydroxide ion squared, right? And that comes from the from this reaction here. Okay, but we have a value that we can plug in for the magnesium ion. They gave it to us in the question. So we see that 2.06 times 10 to the negative 13 is going to equal 0.059 times OH minus squared. So we can solve for OH minus. So we'll divide the KSP by 0.059 and take the square root. And we end up with 1.87 times 10 to the negative 6 for the concentration of hydroxide ion. So what that means is that any OH minus concentration value higher than this will precipitate our MgOH2. Okay. The next question says, if the concentration of that previous solution was 0.025, what would be the minimum hydroxide ion concentration that would trigger the precipitation of the magnesium ion? Okay, so they're changing our starting value in question B. Question B says, well, you're not starting with 0.059, your initial magnesium concentration is 0.025. Okay, so the only thing that's different then here is the value that we substitute in for the magnesium. So we're still going to have our KSP equal the concentration of magnesium times hydroxide ion squared. And we'll still solve it the same way. 2.06 times 10 to the negative 13 divided by 0.025. We'll take the square root of that, and we end up with 2.87 times 10 to the negative 6 molar would be the hydroxide ion concentration we would need to start precipitating MgOH2. Okay. Now in part C, they're saying as you add hydroxide ion to the solution in part A, your MgOH2 is going to continue to precipitate. Eventually, the hydroxide ion concentration is going to be high enough for the calcium ions to precipitate as well. What is the concentration of Mg2 plus from part A when our calcium ions begin to precipitate? Okay, so in this case, it's almost like we have to work a little bit backwards. First, we're going to figure out what concentration of hydroxide ions that we would need for our calcium hydroxide to precipitate. Okay, so we're going to go through the same process we did for our magnesium hydroxide. We're going to do it for our CaOH2 now. Okay. So our KSP is going to be 4.68 times 10 to the negative 6. And that's going to be equal to the concentration of calcium times the concentration of hydroxide ion squared. So our concentration of calcium ion is 0.011. Okay, now we're going to solve for our hydroxide ion concentration. Okay, and we get 2.06 times 10 to the negative 2. And this is the concentration that our hydroxide ion would need to be before our calcium hydroxide could precipitate. Okay. Now, knowing that our magnesium hydroxide is still precipitating, okay, we can use our new value of hydroxide and our KSP value for magnesium hydroxide to figure out what our new concentration of magnesium is going to be. Because our KSP for MgOH2 is still going to be equal to the concentration of magnesium. And this would be represented, we could represent this as the magnesium that's left after the magnesium hydroxide has been precipitating all this time, times the concentration of our hydroxide ion squared. So we have 2.06 times 10 to the negative 13 equals Mg2 plus times 2.06 times 10 to the negative 2 squared. Okay, so I'm going to solve this. Okay, and we end up with 4.84 times 10 to the negative 10 molar as our concentration of magnesium ion that's present once the calcium begins to precipitate. All right. Let's look at the next question. This one's interesting too. This is the complex ion equilibrium that's talked about towards the end of the chapter. And we should talk about a few things. Let's put up the question first so that you can take a look at it, write down what you want. Okay, this is a question we're going to deal with, but we want to talk about a few vocabulary points first, I think. And these are vocabulary points or ideas that you're going to want to pay attention to because they're going to come back around in chapter 26, which is going to be on your exam 4. There's the entire chapter on transition metals and complex ions, coordination compounds, things like that. So this question involves these things that are called complex ions. Your complex ions are going to usually involve transition metal ions that are in solution. Okay. I'm going to pause real quick and write some of this stuff down so that you don't have to wait for me to write it. And then I'll actually go through and explain it. All right, so let's talk this out. First of all, our complex ion equilibria is going to involve transition metal ions. Transition metals are super important in your complex ion equilibria. And that's because your transition metals have those d electron orbitals, and those become involved in these processes. Okay, these transition metal ions, they act as very good electron acceptors. And if you remember back to last chapter, that's going to be the definition of a good Lewis acid, something that accepts electrons. These transition metals are going to interact with what are called ligands. And ligands are either neutral molecules or sometimes they're ions. Whether they're neutral or they're ions, they're going to act as Lewis bases. And they are going to have electrons which they can donate to the transition metals. Okay, so these ligands are going to act as your Lewis bases. Your transition metals are going to act as your Lewis acids. And the ligands are going to surround your central metal. And whenever you have a metal ion that's attached to one or more of these ligands, so the metal ion is going to have one or more of the ligands surrounding it, these new ions are called complex ions. Right? Now, what we're concerned with right now is what's called the formation constant of the complex ions. Okay, and the formation constant is just another equilibrium constant, but this equilibrium constant is specifically associated with the formation of a complex ion. So how likely is it that a particular complex ion is going to form? The larger the Kf value, the larger the likelihood that that complex ion will form. Okay. So that's kind of what we need to know about the complex ion equilibrium before we can start with this question here. Well, I have one more example here of something that I can write down for you just as a demonstration of what the Kf value is, since it's not something that's really talked about until the end of this chapter. If you have something like the complex ion we're going to look at the formation process of this, of Ag, and this is a parentheses, and it's going to be NH3 2 plus. Okay, so this is a complex ion because you have one silver that's going to be acting as your metal cation, and you have two ammonias, and these ammonias are going to act as ligands. Okay, so the formation of the AgNH3 2 plus looks like this. So you have Ag H2O 2 plus, which is aqueous, and this is another complex ion. This is your central metal, and the water is the ligand in this case. Plus 2 NH3 yields Ag NH3 2 plus plus 2 H2O. Okay, and the Kf for this process is going to be 1.7 times 10 to the 7. Okay, so if I wanted to write out the Kf expression for this, for the formation of the AgNH3 2 plus, Kf equals the concentration of the products divided by the concentration of the reactants raised to any coefficients, not including solids or pure liquids. Okay, so Ag and H32 plus divided by Ag H2O plus times NH3 squared. Okay, and that would equal your 1.7 times 10 to the 7. Okay, so it just, your complex ion formation uses the law of mass action the same way that your equilibrium constants did. Okay, and now for real, we can look at this question. I just wanted to make sure that we were on the same page with that. Okay, so we're going to look at Cu2 plus 4 NH3 gives us Cu NH3 4 2 plus aqueous Kf 1.7 times 10 to the positive 13. This Kf value is super high. That means this is going to be very likely to form. Okay, so this question tells us that we're mixing 200 milliliters of a solution that is 1.5 times 10 to the 3 molar. 5 times 10 to the negative 3 molar in CuNO3 with 250 milliliters. Sorry, that should be like a comma. 250 milliliters of a solution at 0.20 molar NH3. They want to know, after the solution reaches equilibrium, what concentration of Cu2 plus aqueous remains, right? So the first thing that we want to do here is kind of figure out what our equilibrium concentrations are going to be, right? That kind of makes sense. We want to figure out not equilibrium concentrations, our concentrations for our ice table. Okay, so we have Cu2 plus, we have NH3, and we have CuNH3 4. Okay, and I'm going to use an ice table to track the changes that are happening as these things react. Now I'm mixing two different volumes together, so I can't just pull my concentrations down and throw them into this initial row. Okay, because I'm adding two volumes together, I have to recalculate the concentration of both of my components. Okay, so I have a total volume of 450 milliliters or 0.450 liters. Okay, so I need to calculate the moles of my copper and the moles of my ammonia. So to do this, I'm going to convert this into liters. I'm going to multiply it by my molarity. Okay, so 0.2 times 1.5 times 10 to the negative 3 is going to be 3 times 10 to the negative 4 moles. And then I'm going to divide that by 0.450 liters. And I get an initial concentration of my copper ion of 6.67 times 10 to the negative 4. Okay, and now for my NH3, 0.25 times 0.2 is going to be 5.0 times 10 to the negative 2 moles over 0.450 liters. And that's going to be 0.11. Okay, and we'll say we have none of this to start with. All right. So now we are going to look at the changes that are happening here. And there's an assumption that we have to make here because we're working with the formation of the complex ions. We have to look at this KF value. Okay, now because this KF value is so large, and this is a very important concept that we have to, or connection that we have to make here. And it's so much larger than the concentration of the copper that we have here, particularly. We're going to be able to assume that almost all of the copper ion is going to be used up. Now, that's not entirely true. Okay, there is going to be a tiny, tiny, tiny bit left, but to make the bulk of our calculations, we can assume that most of that copper will be used up. Okay, and because we can assume that most of the copper is going to be used up, we're able to use the concentration of copper as the change that occurs in our reaction. Okay, so instead of writing, minus x minus 4x, because we don't want to forget our coefficient there, and then plus x, where these x values are, we're going to substitute the concentration of the copper ion in there. Okay, because it's the smaller of these two values. That's why we're focusing on this one. This one's so small, so much smaller than this one, that almost all of this is going to get used up because our KF value is so large. The reaction is so much favored in the forward direction. Okay, so we're going to do minus 4 times 6.67 times 10 to the minus 4. Okay. And even though we're putting this value as our X value for the NH3 and the complex ion that's forming, we still know that we're not subtracting all of our copper out. Okay, even though this is going to be like a minus X value here, we don't know what our equilibrium value of copper is going to be. It's going to be very tiny, but we don't know what it is. We subtracted almost all of it back out. There's going to be a little bit that's left over. So first we're going to take our 0.11 and subtract 4 times 6.67 times 10 to the negative 4. Okay, and we're going to get 0.108. Then over here we're going to get 6.67 times 10 to the negative 4. So now we're going to use our Kf expression and we're going to figure out what the equilibrium concentration of copper is, this tiny, tiny amount of copper that's left. Because you know that Kf is going to be equal to the concentration of our complex ion divided by the concentration of copper times the concentration of NH3 raised to the 4th power. Okay, so the concentration of our copper is going to be equal to the concentration of our complex ion, 6.67 times 10 to the negative 4, divided by our Kf value, divided by our concentration of NH3 raised to the 4th. Okay, and that Kf value is right there. Just plug it in. So at equilibrium, our copper concentration is going to be excuse me, it's going to be 2.9 times 10 to the negative 13 molar. Okay. All right. Okay. So to finish up, I have a few of the conceptual connections from the textbook that I picked out that we can talk about. So let me share my screen again. And I'd recommend you pausing as we go along and really trying to think these things out. You do want to make sure that you can answer all of them. And the conceptual connections are a good way to test your own knowledge as you're going through the chapter. So in this first question, it's asking us which solution is a buffer. Okay, so remember that when you're looking for a buffer solution, you're looking for either a weak acid and its conjugate base or a weak base and its conjugate acid. What you're never looking for is a strong acid or a strong base. So any of these choices that has a strong acid or strong base component should be immediately discounted. Okay, so HCl, nope. HNO3, nope. All right, so now we're down to choices C or D. In choice C, we have HNO2, which is a weak acid. Now the other component would have to be its conjugate base. The conjugate base of HNO2 would be NO2 minus. NaCl is not the conjugate base of HNO2, so we can't, that one's not correct. In choice D, however, the other component is NaNO2. When NaNO2 breaks up in solution, it forms Na plus ions and NO2 minus ions. NO2 minus is the conjugate base of HNO2. So that is the buffer solution. Okay. For this question, they're asking, they say a buffer contains the weak acid HA and its conjugate base A minus. The weak acid has a pKa of 4.82 and the buffer has a pH of 4.25. Which statement is true of the relative concentrations of the weak acid and the conjugate base in the buffer? And again, I would like you to take a minute and try to figure this out before you watch the explanation here. But what you can do to solve this is you can look at your Henderson-Hasselbalch equation to help you out here, to help guide you. You know, your Henderson-Hasselbalch equation says that the pH of a buffer solution is going to be equal to the pKa plus the log of your base concentration over your acid concentration. Okay, so in this case, if we want to use the terminology that they're using in the question, we can say the concentration of A minus, that would represent our base, and the concentration of our acid would be represented by HA. All right. They told us the pH. They said it was going to be 4.25. And they said that the pKa is 4.82. Okay. So obviously, if our pH is 4.25 and our pKa is 4.82, then this expression here in our Henderson-Hasselbalch equation is going to have to be a negative number. For our pH to go down to 4.25 from 4.82. All right, hopefully that makes sense. And if if you're still not sure, then try some numbers out for yourself. Okay. They're giving you three options here. HA is greater than A minus. HA is less than A minus, or HA is equal to A minus. Right away, the one of these that you should be able to get rid of right immediately is this. Because if HA is equal to A minus, then this expression would be the log of 1, right? Because if the concentration of A minus was 2, and the concentration of HA is 2, 2 divided by 2 is 1. The log of 1 is 0. And 4.25 does not equal 4.82. So this one can't be right. Okay. And that's how I like to solve these things if I don't know them. If I don't know them right away, I'll try them out for myself. I'm gonna try out a concentration, the log of something, just a set of numbers where HA is going to be greater than A minus. Okay, so how about the log of 1 over 2? And in this scenario where HA is going to be less than A minus, I can do the log of 2 over 1. Okay. Whichever one of these scenarios gives me a negative number, that's going to be the correct scenario. Okay, so the log of 1 over 2 is negative 0.3. The log of 2 over 1 is positive 0.3. So I can tell just from this, I just pick these numbers at random. It doesn't matter what numbers that you plug in here. Any numbers that you choose, as long as your base value is smaller than your acid value, this expression is going to be a negative one. When your base value is larger than your acid value, then this value is going to be a positive one. Okay, so out of these choices that I'm given, the correct choice has to be the one where my HA value is larger than my A minus value. My base value has to be smaller than my acid value for that log term to be a negative number and for my pH to equal 4.25. This question says a buffer contains equal amounts of a weak acid and its conjugate base and has a pH of 5.25, which would be a reasonable value of buffer pH after the addition of small amounts of acid. So if I'm adding a small amount of acid to a buffer solution, the first thing I should be aware of is that my pH is going to be decreasing. Okay, because adding acid decreases your pH. So right away, choices C and D would immediately be eliminated. Okay, I'm choosing here between choices B and A now. And I have to remember that this is a buffer solution and buffer solutions minimize pH changes. So if I'm adding a small amount of acid, I should only see a very small decrease in my pH. So we can reasonably assume then that the new pH would be around 5.15. Okay, this question says a 1 liter buffer solution is 0.1 molar in HF and 0.05 molar in NaF. Which action will destroy the buffer? Okay, so this requires a little bit of thinking. Okay, which action destroys the buffer? You have to know what destroys a buffer before you can really answer this question. And the main act that will destroy your buffer is going to be using up all of one of the components. Okay. So this is what will destroy a buffer. So in this case, I have a 1 liter buffer solution. So if I want to look at my moles of HF that I have, that's going to be 1 liter times 0.1 molar. So I have 0.1 moles of HF. And my moles of F minus, which comes from my NaF, right? Because remember, my NaF is going to separate into Na plus, which is neutral, and F minus, and this is the conjugate base of the HF. So I still have 1 liter of solution, and I have 0.050 molar, which means I have 0.050 moles of F minus. So I have to look at the choices that they gave me in this question and see which one of them is going to destroy my buffer when I add to it. If I add 0.050 moles of NaF, let's start with the NaF. NaF is the same thing as me adding 0.050 moles of F minus. Okay, I'm adding more F minus in this case. So that's not going to destroy my buffer. So the NaF would preserve my buffer. It would help my buffer out. It would make it a stronger buffer because I'd be adding more of this conjugate base component. If I added 0.050 moles of NaOH, the OH minus component, which is a base, would react with my HF and it would use up some of my HF. But I have more HF than the NaOH that I'm adding. So even after my NaOH reacts with my HF, I'll still have some of my HF left over. So in this case, the NaOH would not destroy my buffer. Okay. I saved the best for last, obviously. If I add 0.050 moles of the HCl, that H plus, the 0.050 moles of H plus, is going to react with my F minus, and it's going to use up all of the F minus that I have available. Once all of the F minus is used up, then that destroys my buffer. So in this case, that HCl addition would destroy the buffer. Okay. This question says the amount of strong acid in the flask here is shown to be titrated by a strong base. Which mark on the burette next to the flask indicates the amount of base required to reach the equivalence point? So remember that the equivalence point is when your moles of your acid is equal to the moles of your base. So in my flask, I have 1, 2, 3, 4, 5, 6, 7 moles of H plus. I would need to add exactly that many moles of base to reach equivalence. So I can count this then. 1, 2, 3, 4, 5, 6, 7. So when the burette, when I've added up to this much OH minus, that's when I've added the equivalent amount of hydroxide ion, and I will be at the equivalence point. Okay. This question says, what is the pH at the half equivalence point in the titration of a weak base with a strong acid? The pKb of the weak base is 8.75. Okay. I mean, oh, I didn't mean to click on that. We'll have to solve for that. Hold on. Got ahead of myself. Okay, let's look at this. All right. Okay, so we're going to look at this. What does it say? Half equivalence. And the pKb is going to be 8.75. Okay, so we need to remember two things here. One, the definition of half equivalence, and this is when the moles of the acid that we're adding are going to be equal to 1/2 the moles of the base that we started with. Okay. And at half equivalence, what ends up happening is that after the moles of acid that we're adding react with the moles of base, we're going to end up with an equal amount of your weak base and its conjugate acid. Okay, so let me just demo for you. I'm going to make up some numbers here, but just to demonstrate the point. If I have a weak base and I'm going to be adding a strong acid to it, what I'm going to end up with on the product side is the formation of water and the formation of the conjugate acid. Okay, so I'm going to have my weak base. It's going to form the conjugate acid and water. All right, so let's say I started with 10 moles of my weak base. And at half equivalence, the moles of acid that I'm adding is going to be half the moles of the base that I started with. So this is before the addition. The addition that I'm going to be making will be 5 moles of the H plus, the hydrochloric acid. So now after that addition is over, obviously I'm using up all of my H plus. right? Because it's the smaller of these two values, and I'll have none left. And I'll have used up 5 moles of my weak base, right? Because I had 10 moles, 5 moles of the H plus reacted with it, using up 5 moles of it. So I have 5 moles left. At the same time, when these two things were reacting and my H plus was using up my weak base, it was also forming the conjugate acid over here. Okay. In my Henderson-Hasselbalch equation, this says that I can find the pH of a solution as long as I know the pKa, and then the concentration of my base over the concentration of my acid. At half equivalence, these two values are always going to be the same. Okay, these are always going to be the same when I'm at my half equivalence point. So this expression at half equivalence is the log of 1, and the log of 1 is equal to 0. So at half equivalence, this part of my Henderson-Hasselbalch equation drops out. So if I want to know what the pH of my solution is, I only need to know the pKa. In this case, they gave us the pKb. So 14 minus the pKb is going to give me my pKa. So 14 minus 8.75 is 5.25. And 5.25 is going to equal my pH, because pKa is going to equal pH here at half equivalence. All right. Next question. Consider these titrations. The titration of 25 milliliters of a 0.1 molar monoprotic weak acid with 0.1 molar NaOH, then a diprotic weak acid with 0.1 molar NaOH, and then the titration of 0.1 molar with strong acid with 0.1 molar NaOH. And it says, which statement is most likely to be true? Okay. All 3 titrations have the same initial pH. All 3 titrations have the same pH at their first equivalence points, or all 3 titrations require the same volume of NaOH to reach their first equivalence points. It's a good question. Okay, you have to think these things out. I'm going to tell you right off, this is going to be our first answer, or this is going to be our correct answer rather, and I want to go through one at a time of why that's true. All right, so we can't say that all 3 of these titrations are going to have the same initial pH, because we can't directly relate the concentration of weak acids with the hydrogen ion concentration, which is what we would use to calculate the pH. For our weak acids, we would have to put this concentration value into an ICE table and use that ICE table to calculate the hydrogen ion concentration and then calculate the pH. Okay. The same is going to be true for your pH of your first equivalence point, right? The pH values are going to be linked to the hydrogen ion concentrations, and these are not going to be the same for all 3. Now the moles of the NaOH that you're going to be adding, that will be the same. Okay. And if you know the molarity of the NaOH and you know the moles of the NaOH, then the volume of NaOH that you'd be adding to get to that first equivalence point, that value would be the same. So the concentration values of your H plus wouldn't be the same, but the amount of NaOH that you're going to be adding to your titration to get to that equivalence point would be the same. This question asks, in which solution is barium sulfate most soluble? This question is asking to look at the idea of the common ion effect and how that changes the solubility of a compound. Anytime you have a common ion present, that's going to reduce the solubility of your solid. So when you're looking through these choices and you see, for example, in choice A, the barium ion is present here. The existence of the barium ion here is going to reduce the solubility of the barium sulfate. In choice B, the existence of the sulfate ion and the sodium sulfate will reduce the solubility of your barium sulfate. So only in choice C, where there is no common ion present, now you would not have any kind of hindrances to trying to dissolve your barium sulfate. All right. And question 9. This question says the solution contains equal concentrations of these 3 ions. When potassium sulfate is added to the solution, which cation precipitates first? So potassium sulfate is going to have the sulfate ion attached, right? So it's going to be releasing the sulfate ion into solution. And these are the 3 potential solids that will form. Okay, so we're going to use these KSP values that are given to figure out which would precipitate first. And like we talked about in the previous example, when you have a very low KSP value, that means that your solid is going to more readily form. Okay, so a KSP value of 10 to the negative 10 means that you need very low concentrations of barium and sulfate in order for a solid to form. So your barium ion would precipitate first in this scenario, followed by your lead ion, followed by your calcium ion. Okay. And that's all the questions I have for you for this chapter. So I hope that you find this helpful. Always can, email and ask us any questions that you have as you're going through these. If we can help clarify any more, we will. All right, good luck. Study hard.